All right, so this is going to be the practice problems level 2 for the class of reactions of SN1 through E2. And in this video, we're going to be focusing on practice problems that have either rearrangements, so carbocation rearrangements that happen through hydride shifts or methyl shifts. And then we're also going to be taking a closer look at how to draw products for E2 reactions when we have an antiperiplanar elimination. All right, so for these problems, I'm going to skip how we determine what type of reaction it'll be, and I'll just label what type of reaction we'll get. And then we'll go from there. And the first couple are going to be those carbocation ones, and then the last part is going to be those E2 eliminations. All right, so for this first one, we know that this is going to be SN1 or E1, mostly because we have a weak nucleophile here. And so to determine if we can get a carbocation rearrangement, we want to draw the intermediate that forms when we have that iodine leave. And so I'll draw out that carbocation here. And so here, the next step of what we want to do is determine what type of carbocation we have. And so here we can see we have a secondary carbocation. And so whenever we have a secondary carbocation, we want to pause and see if we can get a rearrangement that would let that secondary one become a tertiary one. And so for that, we want to take a look at the nearby carbons. And so here we can see that this purple carbon right here has a position where we could potentially have a tertiary carbocation. And so to get that tertiary carbocation, we would have that this hydrogen, which is drawn in here, could shift over. And so we would get a 1,2 hydride shift. And so we end up with a carbocation at that tertiary position. And that initial hydrogen is now bonded to that carbon that initially had that carbocation. And one thing I want to note here is that even though this methyl group here was dashed, when we draw the carbocation, we have to draw this line as straight and not dashed, because the carbocation becomes planar. It has trigonal planar geometry. And so we don't draw a wedge or a dash at that position anymore. We just draw it in plane. All right, so from here, we can then draw out the products. And again, I'll kind of go through this pretty quickly because I think the purpose of this video is mostly to draw in those carbocation shifts. And so we'll get this product as our SN1 product. And then we can also potentially get some of those elimination products through E1, though with a pretty small nucleophile, we'd probably favor our substitution here. All right, and we actually have a lot of symmetry in this molecule, so we're not actually getting a lot of different products here. All right, so that's the first one. Next, let's take a look at this next one. And so here I'm going to do the same thing first. I'm going to start off with that bromine leaving and drawing in that intermediate where we have a carbocation. And so here, I'm going to label this as secondary. And again, whenever we have a secondary carbocation, we want to pause and see, can we form a tertiary one? And so here, we can't actually get a tertiary carbocation because there's no place for us to move or shift over on those nearby carbons that would form a tertiary one. However, what we notice is that if we take one of these hydrogens from the carbon to the left and shift it over, and so similar to that first one, we have a 1,2 hydride shift, we end up forming this carbocation, where it's still secondary, but what we notice now is that this carbocation is resonance stabilized. And so secondary plus resonance. And that's because this ring that I just highlighted in orange, we could draw resonance structures that delocalize that positive charge throughout the ring. And so this carbocation actually ends up being more stable than the original secondary just by itself. Secondary plus resonance is really, really good. It's much more stable than just secondary by itself. And so even though we're not going to tertiary, that additional stabilization from resonance provides a a more favorable carbocation intermediate. And so we're going to end up getting a rearrangement in this case. And so from here, we can next draw in our products. And similar to that first one, we'll have primarily the substitution product where we add on an OH to the position adjacent to the ring. But then we could also get the E1 product here. But again, that E1 is going to be less favored than the SN1 product, just because that nucleophile is pretty small. All right, let's do this next one. So here, same thing. We're going to kick off that chlorine, form a carbocation. And again, similar to all these other ones, we have a secondary one. And the reason these are all secondary is because we really don't get rearrangements if we're already tertiary. And we can't form a primary carbocation. So if we had a primary leaving group, we wouldn't go through an SN1 or E1 mechanism because a primary carbocation is so unstable. And so whenever you get a secondary carbocation, that's like when you generally, what you generally associate with rearrangements. All right, so here we can take a look at our secondary one, and we can see that this highlighted in orange position could potentially be the source of a tertiary carbocation. And so from here, we would want to draw in that hydrogen and show a hydride shift similar to the ones above. So from here, we can draw in our tertiary carbocation, where that carbocation is at that center point position. And from here, we would just draw in our products. And again, I usually like to label that it's tertiary just to make sure that we did everything right, that we didn't accidentally form a secondary carbocation that wouldn't be more stable. All right, and similar to above, we're just going to have a bunch of those products that we get. We have that the methoxy group can add on as a substitution. We could get elimination into the ring, and then we could also get elimination into that chain coming off the ring, but that one's going to be less substituted, so it's not going to be, actually it's not less substituted, but in general, the ones within a ring are usually a little bit more stable. All right. We have all of those. These tend to take up a lot of space. Okay. All right. Next, we can take a look at this bottom one. And so here, this one's a little bit trickier because it doesn't have the chlorine, bromine, or iodine that's usually the leaving group. But OTS, Tosla, is really, really good as a leaving group. And so we could have that leaving group leave, and we would form a secondary carbocation. And so from here, we have a secondary one. And so if we take a look at the next door carbons, we have this one on the end, which we know we don't want to move there because that would be primary, not a good position to move our carbocation. And then here, right here on the left, we do actually have a position that looks like it could have a tertiary carbocation. And so for that to happen, we would actually have to have a methyl shift over in this case. And so that entire methyl group shifts over to allow us to form the new tertiary carbocation. And I'm going to highlight this methyl group in green and then where it ended up. And so we can track the position or the new position of that methyl group. And so now we have tertiary, more stable, and now our big group over here is going to be adding on to that carbocation here. And so we could draw out our products. We have this. And then we also can get our elimination product into between those methyl groups. We could also have a elimination go into one of those carbo or methyl groups that's a little bit less of a dominant product or more minor. All right, so those are the ones that we'll have here, and that's it. And one thing I want to point out is that through all of these SN1 and E1 reactions, at no point am I denoting stereochemistry in the final products, because all of these proceed through that carbocation intermediate, and so we get a mixture of substitution products where we can have the incoming group be either wedge or dash. And so instead of drawing out all the different combinations, we instead just use in-plane geometry to show that it's a mixture. All right, let's do our last one here. So here we have an iodine. We're going to kick off that iodine and form a carbocation here. And so here we have a secondary one, and we can take a look at the adjacent carbons on both sides. And so if we were to form a carbocation, this carbon, it would still be secondary. And so there's no benefit to shifting over to that direction. We don't really care about it. We're not going to do that. However, if we shift over to this top carbon over here, to this position, we actually get some resonance stabilization from this double bond. And so we can do a hydride shift from one of the hydrogens on that top carbon. And so we get a hydride shift to form a resonance stabilized carbocation here. And so from here, we have secondary plus resonance. And so we know that that's going to be a favorable carbocation shift because it's more stable. And then finally, we can draw in the products where with that H2O, really just drawing in the OHs, and then we have the elimination product that forms two double bonds that are conjugated. All right, so that wraps up the carbocation rearrangements, and now we can move on to looking at E2 eliminations, where we have to identify in which direction would the elimination will happen based off of the availability of an antiperiplanar hydrogen. And so what you'll notice is that for all of these, I just chose a strong, bulky base that favors elimination. So OT butoxide is too big and bulky to really substitute efficiently. And so basically, we're always going to get an elimination reaction whenever we see this reagent. And the other component to this reagent is that we have potassium or sodium instead of a hydrogen here. And so we know that this separates out into the positive and the negative because we have an ionic bond between the potassium and the butoxide part. And so this negative charge makes it strong. And so it's a strong, bulky base that favors elimination. That's why I chose that reagent for all of these problems. But going back to our E2 mechanism, as a reminder, we need to have an antiperiplanar hydrogen available for elimination. And so that means that if on this ring, this bromine is dashed, then we need to have a wedged hydrogen that's on the beta carbon of that leaving group. So here we have the alpha, and then we have two potential beta carbons here. And so for each of these beta carbons, we can draw in the missing hydrogens so that we can identify which one would allow for elimination. And so I drew in all of those. And so again, since we have a dashed bromine, we're looking for a wedged hydrogen. And so the only wedged hydrogen that we can see is this one that I highlighted in green. And so our product is going to eliminate into that direction. And that will be our product here. And so even though, let's say that we did want to eliminate down to that top carbon, and we formed this product here, some of you might have drawn this product because it appears like this bond is more substituted. And so with a lot of elimination products, we want to draw the more substituted product. However, here, we can't eliminate to that top carbon, even though this is the more substituted double bond that could form. And so this product does not form because it does not have an antiperiplanar hydrogen that's available for the elimination reaction. And so we do not form that more substituted one in this case. And instead, we're left with that less substituted one that forms from the elimination with that wedged hydrogen. All right, for this next one, we can identify our leaving group, which is the iodine. And then we're looking for a wedged hydrogen on a beta carbon. And so for this, we'll draw in those hydrogens. So both of these are going to be dashed. And so here, we actually get no reaction because we don't have a wedged hydrogen that's available for antiperiplanar elimination with that iodine. And so we have no wedged H's. That would be anti to that iodine. And so we get no reaction here. All right, next one, same thing, identify our leaving group and identify the available hydrogens on beta carbons. And so on this one, on the left, we have a wedged and a dashed hydrogen. And here, for this one, this carbon, we actually don't have another hydrogen because this carbon, I'll zoom in here. So this carbon right here already has 4 bonds. We have 1, 2, this hydrogen, and to the left. And so there's no dashed hydrogen that we would add to that carbon. And so we just leave that one be. There's no additional hydrogens that we can draw in here. And so to get our elimination, we want to look for a dashed hydrogen because our initial starting group is wedged. And so for that, we can see that we only have this one to the left available. And so we could draw out our product with the double bond going that direction. And that will be our product here. One really common mistake I see people making with these like fused rings is sometimes drawing a product that looks like this. And this is a mistake that people make for both E2 and E1 eliminations, where they will draw a product like this. And then there's also a hydrogen that's coming off here. And the reason this product doesn't work is because this carbon, the one highlighted in green, has 5 bonds. We have 2 double bonds here, one going to the right, one going down, and then this hydrogen. And so make sure you're keeping track of the number of hydrogens on your products, especially for these kind of ring systems where it might be a little bit trickier to see if a carbon has 4 bonds or not. All right, let's do this one. So here we have a base, we have a bromine, we have our leaving group. And so here we can identify our alpha, and then our beta carbon right here. We only have 1 in this case. And so we're looking for a hydrogen on that beta carbon. And so here we actually see that we don't have a hydrogen available on that beta carbon. And so the process of looking for that antiperiplanar hydrogen doesn't work. We don't need to even do that because we don't even have a hydrogen that's available for elimination. And so here we're not going to get an elimination reaction with this reagent because we don't have a hydrogen available on that beta carbon. All right, this last one's a little bit tricky. So here we have our bromine leaving group, and we can identify our beta carbon right here. This phenyl doesn't have a hydrogen available. If we were to draw out the structure, it would just be like the ring like that with no available hydrogens. And so we can ignore that one for the purpose of, or that direction for the purpose of this question. Next, we want to draw in all the hydrogens on the beta carbon. And so we have a wedged one here. And so here we can see that this hydrogen and the bromine are not currently drawn, are not antiperiplanar to each other. It's not that one is wedged and the other one is dashed. And so to get the right elimination, we have to rotate around the center bond right here to allow for those hydrogens and bromines to be on opposite sides of each other. In comparison to these ring systems, in rings, we don't get free rotation around those bonds. So we're locked into the orientation that we're given. We can't rotate the bond to change the wedge or dash orientation of one of the substituents. However, in these problems where we do have free rotation, we can freely rotate around that middle bond. And so what we can do is redraw this molecule. And I'll just redraw it to the right here, where we keep the left side the same. But then we rotate that bottom carbon around so that the bromine is dashed. So I'll draw in the hydrogen here on the left, or right carbon too, just so we can keep track of it. And so what that changes is that this hydrogen ends up being in plane, and that phenyl ends up being wedged when we rotate. And we can think of it as just like everything's just moving over one position on the rotation. And I'll actually, in my drawing, I'll swap these just so it's a little bit easier to tell. So I'll put the phenyl like that and the bromine here. So we just basically shifted them all over one position going counterclockwise. All right, so now from here, what we can see is that this bromine is dashed and this hydrogen is wedged. And so those can now eliminate in a antiperiplanar fashion. And so when we draw our product, we get the double bond here. And those phenyl groups are on the same side. So we can see that in this structure, that hydrogen in this group are on the same side of the bond, while the phenyl are on the other side of the bond. And so note that this is not the same as this product. So if you drew out this product would be incorrect because it doesn't have the correct Z and E denotations for that alkene. And so you have to draw this top one that I have up here as the correct product for this reaction. All right, that wraps up this video. If you haven't done so already, I recommend doing the practice problems in level 1. And then I also have some mechanism questions for level 3, along with some more advanced problems related to this concepts covered in this chapter.